Hey guys, so welcome to my YouTube channel. In our last video, we discussed about electric field 1, where I made basic introduction to different concepts in electric field. I think I talked about electric current, I talked about potential difference, and I gave example of different type of circuits. We have open circuits, closed circuits, and short circuit. So in today's lesson, we're gonna talk about electric field 2, where I will talk about conductors and insulators. I'm gonna talk about electric circuits, and I'm gonna talk about parallel and series connection in an electric circuit. So I'm going to go on with this series for I don't know how long, but probably I'm still going to have two more videos on electric field because I feel there's a lot to cover in this particular subject. But so let's start for today. So I'm going to start with conductors and insulators. So in an electric field, I said is a space or region whereby electrical properties or electrical phenomenon is being experienced. Just like you have a football field where they play soccer, that's what they do on football field. Same thing. What happens in an electric field is electrical phenomenon or electrical force is being excited on the in the field or is being experienced in the field. So for this to happen, there are materials that actually can conduct electricity. There are materials that can there is a medium in which these electric forces can actually display their properties. So for example, in a basketball court, they can only play a basketball ball, right? In a soccer pitch, that is a football field, they can only play a soccer ball. They can play a tennis ball. They can play a table tennis ball. Same thing in an electric field. We have materials that we call conductors. Now, without these conductors, we cannot have electric field. These conductors serve as a primary means or as a medium whereby electric forces display their phenomenon or they displays their characteristics. And so I will, in a simple way, I'm going to define conductors as materials materials that allow that allows materials that allows electricity to flow through them easily, through them easily. It's as simple as that. Or you can just say they are materials that allow electric field to display its phenomenon or its properties. It's as simple as that. So we have examples of conductors. We have copper, we have silver, we have inorganic materials or inorganic acid solutions and all. So like your copper wire, we have silver wire, we have platinum and all. So we have uh these examples of materials that actually conduct electricity. So we call them conductors, and each of them they have different properties which I'm going to explain later in my other videos. They have different properties, they have what they are used for, they have what they are not used for. For example, the wire that is being used for your earpiece, is different from the wire used for your um, your charging devices, just like your mobile phones or your notebooks or your laptop or your iPad or whatever. They have different wires, different capacity of electricity that can pass through them. They are designed in different medium. So that's it on that. So let's move to insulators. Insulators is the opposite of conductors. So insulators are materials that never allow never allow electricity to pass through it. Yeah, to pass through it. So example of this is like plastic. Plastics, they don't allow. We have glass, we have wood, like your furniture. These things, we never allow electricity to display its phenomenon or properties in an electric field. It will never happen. So that is that on what conductors are and what insulators are. So these are basic concepts. They are material mediums whereby we need to explain before we go into further illustration or further explanation of what happens in an electric field. Now I'm going to go to electric circuit. Now, electric circuit. Now, in an electric circuit, is how will I explain? Is a complete set, of or a basic form of how to introduce and or of how to introduce an electric design. I'll put it that way. So in an electric circuit, we have a power supply. So we can have complex electric circuits. We can have extremely simple electric circuits. We can have less complex and all. So it depends on whatever use you want to use your electric circuit for. You cannot compare the electric circuit of of a bungalow, a very small house, to an electric circuit of 5 or 4 or 6 story buildings. It is definitely going to be different and more complex. So I'm just going to use a very simple one to explain electric circuits. So in an electric circuit, we can have our power supply, which can be, a dam power supply, We can have solar system or solar energy. We can have our battery. We can have our electricity. Any form of power supply that can generate power. Yeah, so it depends. We can have solar, we can have the battery, we can have the electricity. I think these two are kind of, they all generate electricity. So depends on whatever is going to provide your power supply. We can have coal. We have different ways to generate power supply. We can have power from coal. I think this dam power supply is power from turbine. And all. So we have power supply in our, and we have what we call voltmeter, which measures the volts. Voltmeter measures voltage that passes through your circuit. Then we have ammeter, measures your current. This measures the current. And what else do we have? We have key, or I call it switch, which I'm very sure everybody know what switch mean. You on and off. So these actually control the flow of current, or the flow of power supply, controls the flow of power supply. Yeah. Yeah, controls the flow of power supply. What else do we have? I think then we have wire, definitely. We have a conducting wire, which is our medium for electricity to pass. It can be copper, it can be silver. I think silver is the best conducting. Yeah, the best conducting, metallic conducting is silver, then followed by copper. But silver is pretty expensive, so most of the time people use copper. So now I'm going to draw a simple electric circuit, to explain everything I've, which is going to contain power supply, voltmeter, your ammeter, a switch, and a conducting wire. Now, so let me draw that. So here we have A, then goes here. So this line is assumed to be our conducting wire. So we have something like this. V. Oh, I forgot to mention one more thing, but I think then we have a resistor R. Then then we have a power supply, which is our battery. Then we have a switch here. It goes this way, right? Okay. So I forgot to add resistor. I think let me add it here. Resistor or load. Let me call it load. Yeah. So now we can see from this simple circuit. So this is our battery, plus negative, supplies a current. Now this current flows through an ammeter that measures the amount of current that passes through. Now it goes into this resistor. Now this resistor can be a load. This resistor means something that takes a little out of the current that passes through here. So for example, if I decide to change this resistor to a bulb, or I change it to a charger that actually charges a device, it means that if, for example, if 5 ampere flows through here, it means that this charger is going to consume some current out of this 5 ampere. So that's what a resistor acts in this circuit, or I call it load. Yeah, so that's what I mean by that. Let me clean this up. So we have a voltmeter too, which actually measures the voltage across this resistor. Then I'm going to explain why our voltage is being connected this way and why our ampere is connected this way. I mean, why can't we have voltage here? Why can't we have? So there's a reason for that, which I'm going to explain sooner. So this is simple circuit. Doesn't look much simpler than this. So now my third outline for today is for this video is parallel and series connection. Now that is going to explain why we connect our ammeter this way and we connect our voltage this way. So why we connect our ammeter this way is because when current flows through, when current is being supplied from our battery, we need to measure the current directly right before going into our load. Now, why we measure the voltage now? Because we need to know the voltage that is being consumed by our device. So that's why voltage is being connected in parallel. Voltage, voltmeter, let me put it that way. Voltmeter is being connected in parallel to the resistor, or load, while ammeter is being connected in series to the resistor or load. So for direct measurement of our current, we need to connect our ammeter in series, and for us to know the voltage that passes across our voltmeter, we need to connect our voltmeter in parallel. Now let me talk about the final thing I'm going to talk about today in this video. So we have parallel, and I'm going to solve a lot of questions too. We have parallel and series connection. Now in an electric circuit, we can either connect our wires or our load or our bulb in parallel and in series. Now I'm going to show what parallel is, and I'm going to show what series is. Now for example, if we have a bulb, don't mind my bulb. Alright, so there's a wire passing through. We have a bulb, we have a bulb, we have a bulb, we have a bulb. Yeah, now there's a wire passing through this bulb. Now current is being supplied. Now what happens? This bulb lights up, right? Same current I passes through everything. Now this kind of connection is referred to as series connection. So let me name this bulb R1, R2, R3. So now if I want to resolve these resistors or these bulbs, so my total will be RT, will be R1 plus R2 plus R3. That makes me know the total resistance that this bulb, or the total amount of the total amount of current consumed by these bulbs, the total amount of resistance consumed or offered against the current that passes through here, right? Now let me give an example of parallel. So parallel, there's always a division here in series. Wait, let me make this thing more better. Okay, so in series connection, we have same current. So know this point, same current passing through the resistors, and we have different voltage passing through the resistor. So let me give you a very good diagram for that. So this series connection, just one straight one wire passing through. Now so we have a voltmeter here, different voltage, voltmeter here, then we have a voltmeter here. So we have V1, V2, V3, then we have R1, R2, R3, then we have just I1. There's no I1, there's no I2, I3, because the statement says same current pass through the resistor. That means I1 passes through resistor 1, I1 passes through resistor 2, I1 passes through resistor 3. And we know Ohm's law, which I'm going to talk about in my next video, but let me just say this. Ohm's law equation is V equals to IR. So if I want to calculate V1 here, that's V1 equals to R1 I1. V2 equals to R2 I1. V3 equals to R3 I1. Same current passes through everything. That's for series connection. Now, how about parallel connection? How about parallel connection? Now, let me draw parallel connection. So we have a current coming through I. Now, this I decided to divide into I1, I2, I3. Now, what series? Same current, same I goes through everything. But in parallel connection, we have the I dividing into I1, I2, I3. So we have this resistor here, R1. We have this resistor here, R2. We have this resistor here, R3. So these K. Now, so this is an example of parallel series. Now, to resolve parallel series is different from to resolve parallel connection is different from series connection. Resolving a series connection is RT equals R2 equals to R1 plus R2 plus R3. So how do we resolve this? So this will be resolving 1 over RT equals to 1 over R1, 1 over R2 plus 1 over R3. Yeah, so this is how we resolve this. Then we find the value of our RT, right? Now this has its own special rule too, which I'm gonna list for you. Like I listed here, same current passing through for series connection, and different voltage passing through the resistor. This for series connection. Then what do we have for parallel connection? We have different currents passing through, different current passing through, and we have same voltage. So it's more like the opposite, same voltage passing through. So if you look at these, you can see different currents passing through R1, passing through R2, passing through R3, but they all have same voltage reading everything here. So for example, if I want to look for, according to Ohm's law, where we have V equals to IR, where V is your voltage, I is current, R is resistance. So when you want to do the reading for this one particularly, so we have V will be I1 R1, then we have V will be I2 R2, we have V will be I3 R3. Remember I said the voltage is what? Same. It means whatever answer I get here is the same as this, is the same as this. Why? Because this voltage is same for parallel connection. So I1 R1, I2 R2, I3 R3 all have the same voltage. But in series connection, we have different voltage, different but what, same current. So that's a major difference between parallels and that's a major difference between parallel and series connection. Now let me work out some example so that this can make sense. So let me like solve the problems. Yeah. So these are just basic, like extremely simple things. These are so simple compared to like the advanced um, way of resolving these things, because we have concepts like Kirchhoff law, we have Kelvin's theorem, we have Norton's theorem, and so on. You know how to resolve all these things. So, but these like a basic thing that everyone can easily understand. So, for example, now if we have this, let me call this example one. All right. So we have 2 ohms, 3 ohms, and we have 4 ohms. Now, if I say resolve the diagram above, simple. I mean, this is a series connection, and in a series connection, I told you RT equals to what? R1. Let's say this is R1, R2, R3 plus R2 plus R3. So RT equals to 2 plus 3 plus 4. This is 5, this is 9, so 9 ohms. It's as simple as that. But though they are more complex diagram, which I'm gonna do, example 2. If I have something like this, yep, and I have 2, I have 3, I have 4. Let's do it that way. Yeah. Now these ohms, and you have to resolve this. Now this connection is, you can see division of your currents, different currents. This is a parallel, so we resolve this by 1 over RT, 1 over R1 plus 1 over R2 plus 1 over R3. So resolving these, we have 1 over RT, we have 1 over 2 plus 1 over 3 plus 1 over 4. So I think if you solve this, let me try and solve this quickly. 1 over 2 plus 1 over 3. You can use your calculator and you can do it manually, whichever ones you want to do. So this is 13 over 12, 1 over RT, and RT will be 12 over 13 ohms. So if we do 12 divided by 13, it's like 0.992 blah blah blah. So you can just put this way. So this is your resultant. So example 3. Now let's go to a more complex diagram. Now if you have something like this, and because we can have both parallel and series in the same diagram. Now look at this. So this is 5 and this is 10. Now these look more complicated now, but it's simple though. So this current starts from here, same current passes through here, and anytime same current passes through, it means they are what? Series. This is series, but when the current gets to this place, it divides. So it means that these two are in what? Parallel. So we solve this in series, we solve this in parallel, then we add them together. Simple. So now solving this in series first, that will be RT will be 3 plus 2. So we have RT equals to 5. Now this is in parallel because there's a division of current that flows here, then divides. So solving this 1 over RT, that's 1 over 5. Solving parallel is always 1 over something. So 1 over 10. So solving that, 1 over 5 plus 1 over 10. So your answer is 3 over 10. 3 over 10, 1 over RT. So RT is 10 divided by 3, which is 3.3. RT is 3.33, and RT is 5. So your total RT will be 5 plus 3.33, which is 8.33 ohms. It's as simple as that. So we resolve these two in series first, these two in parallel, then we added the solution. Now let me do one more or two more. So example 4. So we have something like this. This is a little bit complex, but still solvable. Yep. So drawing this, so we have something like this. Good. So this is 4, this is 2, this is 1. So you can see that we can have complex circuits, extremely complex, but with the basic knowledge, you can solve them. So let's analyze this. Now there's a current coming here, passes through here, and now it divides. It means this is parallel. This will be current pass through here, but when it gets to this point, divides into 2, divides into 1. So this is parallel, then it goes again, then divides again. This is also parallel. Now let's solve this 2. This is parallel, this is parallel. So this will be 1 over RT, that's 1 over 2 plus 1 over 1. 1 over RT, 1 over 2 plus 1 over 1, that's like, I think, 1 over 2, I think. Yeah, so let's solve that. Yeah, 3 over 2, yeah, 1 over 2. Yep, so RT equals to 2 over 3 ohms, which is 0.67. RT equals to 0.67 ohms. So we resolve that. Then let's resolve this. So this will be 1 over RT is 1 over 3 plus 1 over 5 plus 1 over 5. So if I solve this, let me try and solve it. So 1 over 3 okay, so this is 11 over 15. So RT will be 15 divided by 11. RT equals to 1.36 ohms. Yeah, 1.36 ohms. So we've resolved this to be, these two has been resolved to be 0.67. This 3 has been resolved to be 1.36. Now, so this is what our circuit now looks like. We have 4, we have 0.67, and we have 1.36, right? So this current passes through, we resolve these to get this, we resolve these to get this. So now it looks like this. Now it's in series, so which means we can do our output will be 4 plus 0.67 plus 1.36. So if we do this, 1.36 plus 4 plus 0.67, so that's 6.03 ohms. It's as simple as this. I don't know if I should do one more example, but I think with these examples they are pretty straightforward, and you can always check out for more questions to practice by yourself. So thank you for watching. Don't forget to subscribe if you like what you just watched, and put on your notification button just in case I'm going to upload some other videos and you don't want to miss out. So thank you so much for watching. In our next video we talk about Ohm's law, that will be electric field 3. Thank you for watching.